So you were wondering how to integrate when something was more complicated, something along the lines of perhaps, we have the reverse of the power rule. What about the reverse of product rule, quotient rule, chain rule, and things like that? So, yeah, I know. As I could read it on all of your faces. So we're going to look at the reverse of the chain rule called use substitution. I have the process written right here, and it's really actually pretty straightforward conceptually. You could get bogged down on different possibilities for designating your U value, which I'll get into in a minute. But really the big challenge going forward, bless you, the big challenge going forward isn't going to have to do with this individual topic or the individual topic that comes after that, or this and that and the other thing. It's going to come from not getting the different topics confused with one another. All right, so when we learn integration by parts, down the line you'll look at a question and say, how do I know this is integration by parts versus use substitution? All right, that's the key ingredient here. But this is the foundation of the rest of the year. All right, this one topic. Because it conceptually is embedded in everything else we do. That's how important it is. All right, so how do we do it? Well, what we do is we choose a U. So, and that U could be a function such as the inner function of a composite function. If it's exponential, it could be the exponent. If it's a log function, it could be contained it can be contained within the logarithm. Same thing with the trig function, sine of, let's say, x squared plus 1 or something like that. In this case, it looks like it's just the x squared plus 1. But generally what we're looking for is something that is differentiable to the other part of the function. All right, so choose a U such as the inner part of a composite function, but it must differentiate to be a scalar multiple of the other part. So the question would be, well, what do you mean by the other part? So the answer to that would be, well, the part that you didn't choose. So you're going to choose one part of your function to be U, to be the U function. Whatever the other part is, has to be a scalar multiple of the derivative of the part that you selected as U. Right? So it's only off by a constant multiple. So here we have a 2x. If I select this to be my U, its derivative has to be a scalar multiple of 2x, so maybe 4x or 10x or even x, but it has to include the x. If it doesn't, then you selected the wrong U. Right? In the early goings, everything is going to work out. Later on, we're going to have to manipulate algebraically or even trigonometrically to get it into a nicer form so that it does work out. But once you've selected your appropriate U, very easy. I'm going to let U equal x squared plus 1. Trial and errors, at least in the early goings, is not a bad strategy, because if you select the wrong U, you find out pretty quickly. And then you just, okay, well, that wasn't the right U. I'll choose the other thing then, and then start over. All right, so I select my U as x squared plus 1. I'm going to take the derivative of this, which is going to be du dx is equal to 2x. All right, so this differential equation, the du dx equals 2x, is going to help me make a substitution within my integral. All right, so first thing I'm going to do is replace the x squared plus 1 with the u. So this would become 2x times u dx. Now I have an inconsistency here with my variables. I can't integrate yet with more than one variable. So I have x's and u's, and the x's have to go. Right? We're substituting away the x's and introducing the u's. So the 2x and the dx have to go. Now, if you look at your differential equation, du dx equals 2x, with a slight bit of manipulation, put it in differential form, du equals 2x dx. We now have a substitution because 2x times dx is equivalent to du. So that tells me that I can replace the 2x dx with a du. And that's going to give me a u du. So what we did was we transformed our integral from something that we could not anti-differentiate to something we absolutely could. What is the antiderivative of u? U squared over 2, so I'll write 1/2 u squared. Missing just one little thing, plus c. All right. So that u, because what we want to do is reverse substitute at this point, because our answer should not be in terms of u. Our original integral is given in terms of x. I'm going to swap out the u for what it really is, x squared plus 1. All right. So this is just a little taste of the concept of u substitution, just something to get our feet wet. Tomorrow I'm not going to be here because I have to go on yet another conference. Another one. This one I'm actually interested in, so that's good news, I guess. But you're going to work on the textbook assignment for homework. I'm going to leave you a worksheet in class tomorrow. Extra practice on just simple integration. And then on Friday we'll continue. Well, I'll take questions on the textbook assignment, but then I'll also continue with this and give you another look at it. All right. So the key again to u substitution is defining the appropriate u. If you go wrong, you'll find out pretty quickly, and then once you find out, you start over and choose a different u. The idea again is that whatever you select as u has to differentiate to be a scalar multiple of the other part of your integral. Okay? So in the case of number 1, we selected x squared plus 1. Its derivative was 2x. That's definitely a scalar multiple of 2x. The multiple is 1, but it's still a multiple. All right. If I had something like, I identify my u and come up with 2x squared, that's not a scalar multiple of 2x because it's not multiplied just by a constant to get to the value of du. All right. So it has to be only a constant off from being the same expression. All right. So with that in mind, if you're looking at polynomials, you might say, well, I'll just take the thing with the highest power. Let me bring it in a little bit because font-wise it's going to be a little iffy. So I'll let my u be x cubed plus 1. All right. Some people might say, well, why not let it be the entire root? The square root of x cubed plus 1 and get rid of that whole expression. Well, if you do that, then you're going to have to take the derivative using chain rule. And you just play that out in your minds. Are you going to get something as simple as x squared if you were to do that? No. Right? So the thing under the radical is what we want to let be our u. So I'm going to take the derivative, du dx is equal to 3x squared. And that expression is just a constant multiple away from being the other part of my integral, right? Which is what I'm looking for, right? So I want to get this in differential form. So write it as du equals 3x squared dx. Now that's going to happen every time. You take the derivative and then multiply both sides by dx. So then the question, a natural question might be, well, can we just skip this middle step and go right to that? The answer is yes. All right, so take the derivative, it would be du times the derivative dx. All right, just jump right to that step. It saves you a little bit of space. All right. Now, what I want to do is swap out the x squared, not the 3x squared. All right. So I'm going to divide this by 3. All right. There is no 3x squared here to swap out. There's only an x squared and a dx. So if I get rid of the 3, and circle the dx here so it's a little bit more obvious. If I get rid of the 3 here, I have a clean relationship, and that is, I'll write it as 1/3 du is the same thing equal to x squared dx. So that tells me I can replace the x squared dx, I'm sorry, I said that right. The x squared dx with a 1/3 du. Just going to draw some arrows. All right. We already know what to replace the x cubed plus 1 with. That's the same as saying u. We defined it that way. So this would be, if we just put it all together, we would have a 1/3 du. So I'll put the 1/3 here, the du at the end, because when you're integrating, the d part of it goes at the end, one way or the other. I mean, if you put it before, that's fine. Eventually, you're going to want to move it to the end anyway. All right. Instead of a radical x cubed plus 1, it's a radical u. All right. So we've done a complete variable substitution, with the idea being that our new expression is way simpler than our original one. All right. Clean it up a little bit more. 1/3 u to the 1/2 du. Now it's anti-differentiable. I mean, it was before, but now it's much easier to do, right? Because we're looking at something that is just anti-differentiable by the reverse of the power rule, right? So increase your exponent by 1. You're looking at u to the 3/2. Divide by the new exponent. So that would be 1/3 divided by 3/2, but that's the same as saying 1/3 times 2/3. Right, so that's going to be 2/9. All right, plus c. The u has to go away because our original integral was represented in terms of x. I don't want a final answer in terms of u. There will be some topics later on where I actually show you in what circumstances you can leave it in terms of u, but that's for a different unit. So 2/9, instead of the u, I put the x cubed plus 1 to the 3/2 plus c. There's some instances where you can avoid this process, and I kind of fell into that trap early on in Calc 2. It's not pretty, because I ignored all this stuff. I'm like, well, I figure if this is the same as saying x cubed plus 1 to the 1/2, I'll just take the antiderivative of that, then I'll check it, and then I'll just change my coefficients as needed. And that's, you know, sometimes that's a good technique in a pinch, but it really amounts to trial and error. And it doesn't always work because you get to more complicated situations where it's not obvious what the u is and how to make your cancellations, and so everything falls apart. And that usually happens when we get to trig. Right? So the process at this point is what you want to kind of nail down so that when the situations get more challenging, you're not overwhelmed. For number 3, speaking of trig, we have cosine squared times sine dx. All right, so what I want to do here, again, identify the value of u. I'm going to rewrite this because, you know, the cosine squared x notation, it's very popular notation. It's a concise form of notation, but it's not very practical because any kind of software that you see, it really doesn't accept that notation. Right? You try putting cosine squared x in your calculator, you see it doesn't work. All right, so I'm going to write it as parentheses cosine x squared times the sine of x dx. All right. There are a bunch of different possibilities to establish your u. When you're identifying u, you want to be thinking, whatever I'm calling u should differentiate to be the other part of the fraction, other part of the integral. All right, so let's say, for example, and I'm going to play this out the wrong way first. Let's say, for example, I think u is the sine of x. What would my derivative be? Cosine x, so I would say du equals cosine x dx. All right, is that going to help me take the integral that I was given in terms of x and make it completely in terms of u? I just told you this the wrong way, so you know what the answer is going to be, no, right? So I would be able to replace the sine function with a u, but I'm not going to be able to replace both of my cosines, because I have a cosine squared, so I have a cosine times cosine. This will replace one of them, but what I'd be left with, if I were actually to carry out these substitutions, I'd be left with an integral that contains both x's and y's, x's and u's. All right, so that would be a problem, because we don't know how to anti-differentiate yet when you're dealing with two variables within the integral. So that's not going to fly. All right, so here's another wrong way that I found in the past that if I only show the right way in class, when you stumble and you try to pick up the pieces, you don't know what to do necessarily. All right, so here's another wrong one. You say, oh, that cosine squared looks pretty beefy. I'll take that whole shebang. Let's get the whole expression. I want to get rid of that. If I can substitute out something, why not substitute out as much as I can? What would the derivative of that be? Negative 2 sine x cosine x. You know, when in doubt, just throw a plus c in there. Dx. Yeah, it's chain rule, right? All right, so in its almost simplest form, it would be this, because it would be, you have a function raised to a power, so 2 cosine to the first times the derivative of cosine, which is negative sine. And so you get this whole expression. So you might simplify it further and say negative, what is 2 sine x cosine x equivalent to? Sine 2x. All right, it's the double angle rule. All right, so maybe you think, I'm clever. I see through your tricks. All right, so you got to ask yourself, I'm able to, with the u, get rid of the entire cosine x squared. With either variation of my du, I can get rid of, well, actually, with the first variation, I can get rid of the sine, but I'd be introducing a cosine, right? So there'd still be a u and an x in my integral, right? In the case of my modified du, I wouldn't be able to cancel anything because they're not like terms, right? So another false start. If you default to the idea that whatever the expression is that's being raised to a power, or is the denominator of a fraction, or something that's contained within a log, or is the exponent in an exponential function, you know, the inside part. So thinking in terms of composite functions like chain rule, whatever the inner function would be as a default way of identifying u, that's probably a pretty good way to go. All right, so if that's the case, I'd be looking right at just the cosine of x, in which case the derivative would be what? Negative sine x dx. All right, because again, we're applying that little shortcut where we don't write du dx equals, it's du equals whatever the derivative is times dx. Right, we're putting in differential form. All right, so if I'm rewriting my integral, I now know immediately that I can replace, instead of having the cosine squared, it could be just a u squared. All right. Now, it looks like I have to get rid of a sine x. All right. Well, that's a problem. It's not an insurmountable problem. I want to get rid of a sine x. I want to do a direct substitution there, but I have a negative sine x dx. All right. So if that's the case, and I just want it to be sine x dx, what would the left-hand side be equal to? Negative du. We're just negating both sides. So that would be my substitution for the sine x dx. All right, so that's going to go away. Sine x dx is going to get... So I can multiply my u squared by negative du. All right, so in which case we'd be looking at a little slightly simplified form, negative u squared du. Much easier to integrate than cosine squared sine. I mean, if you were to work with it in its original form, it would be guess and check in its most basic form, I suppose. All right, so negative 1/3 u cubed plus c. Increase the exponent by 1, divide by the new exponent, but then swap out the u for what it really is. Which is the cosine function. All right. And so, in all honesty, even in a case like this, you may have with guess and check, you may have guessed right. Because if you're thinking the reverse of the power rule, you have a cosine squared. All right, well, maybe that's going to cosine cubed. So 1/3 cosine cubed. Give it a shot. You'll see that it gives you the exact opposite sign of what you're looking for. So slap a negative on it and call it a day. All right, so sometimes there is value in just making a quick conjecture of over what you think the antiderivative might be. Right? Because it is a time saver, especially if you have two false starts. Right? I don't know what time.
15.
15? Oh, I'm moving right along.
One question.
Sure.
What is the antiderivative of du?
The antiderivative of du, at this point we're just saying that du is part of the set of instructions to tell us to take the antiderivative of the thing that precedes it. All right, but later on we'll see it's actually a way to determine area, and the area model is the antiderivative. But that's a more visual thing, and it deserves its own time in the spotlight. All right, so the u, poor quality u, 1 plus x to the 4th. All right, the reason I selected 1 plus x to the 4th is because that's only a constant multiplier away from being x to the 3rd. And that'll help us cancel out the other part of the integral. So du would be equal to 4x cubed dx, making x cubed dx, which is the thing that we're trying to cancel, equal to 1/4 du. All right, so this is the part where you kind of have to survey the landscape and see what's going on in the integral, what you need to swap out. Because the 1 plus x to the 4th is going to go away just by the presence of u. It's the x cubed that we want to go away. So when I come up with 4x cubed, I need to make an adjustment on that so that it allows me to only cancel out the x cubed and also the dx. All right, so that's telling me that this is going away and it's getting replaced with that. All right, so we're looking at, if I wrote it all ugly like, it would be 1/4 du over u squared. But then if I clean it up, I'm looking at the integral of 1/4 u to the negative 2nd du. The antiderivative of which would be what? Negative 4? 1 over 4? U to the negative first.
4 and then 1/4 du, 1/4 is both bottoms would be 4u squared on the bottom. And then it would be negative 4u to negative 1.
If it's 4u squared on the bottom, when you bring the u squared up, it's only the u that's coming up. So the 4 would stay on the bottom.
Okay.
All right, so we're looking at negative 1/4 u to the negative first. So negative 1/4, 1 plus x to the 4th to the negative first plus c. Very easy to check, again, because all you're doing is applying the rules of differentiation. So in this case, it would be the chain rule. So negative 1 times negative 1/4 would give us a positive 1/4 times 1 plus x to the 4th, and that would go to the negative 2nd, right, which coincides with what we have here, multiplied by the derivative on the inside, which is 4x cubed. Multiply a positive 1/4 by a 4x cubed, you're getting x cubed, right? And so this would verify itself against that once you take its derivative, and so there you have it. All right.